Hello, today we have our first video tutorial on linear response theory, and I believe it's quite important to start with understanding what is the interaction picture, more or less in general terms, not so specific. So the interaction picture, as I said, this will be our first look into linear response theory. This is a very important topic to understand linear response theory, so we will start from here. Now, to understand the interaction picture, we just consider what is the ruling mathematical object of a quantum system in the absence of a perturbation, and as such we write the Schrödinger equation in this way. H0, which is the Hamiltonian acting on the eigenstate psi of t, is just equal to IH bar, the time derivative of psi of t. So then this is the ruling mathematical object of quantum mechanics. We will consider this in the absence of the perturbation. Now, when we don't have a perturbation, I will claim here that this system has an associated quantum expectation value of the associated operator A. The 0 means that there is no perturbation, and this is given by 1 over the partition function times the summation over a set of eigenstates phi 0 e to the minus beta e0 phi 0. So bra phi 0 a ket phi 0. Okay, now let us ask the question, what happens when we actually have a perturbation? So when we have a perturbation, what will happen is that this ruling mathematical object will turn out to be H0 plus a perturbation W of t, see, all acting on psi of t, equal to I H bar, the time derivative of the state psi of t. And this now this quantum system, under the effect of the perturbation, will have an associated operator A whose expectation value is given by 1 over z. Now note that we don't use the subindex 0, summation over a set of eigenstates phi e to the minus beta e bro phi operator A get phi. Okay, so then this is what we have. This is the assumed knowledge for what we're going to do. This is equation 2, and now we will consider the following. Let's say that psi of t evolves in time according to e to the minus I over h bar h0 t times some other eigenstate phi of t that we will just see that is an eigenstate of the this will be an eigenstate of the perturbation, and then we label this equation as equation 3. Okay, now the procedure goes as follows. Let's first calculate the term I h bar, time derivative of psi of t, and see what is this in terms of the state phi of t. Okay, so then let's do this in red, change color as you are used to now, and we do the following. So I h bar, time derivative of phi of t, is equal to I h bar, time derivative of e to the minus I over h bar h0t times phi of t. Okay, and what we have is the following. So we have IH bar minus I over h bar. You can see that this goes to 1 times the Hamiltonian h0, okay, times e to the minus I over h bar h0t times state phi of t. And the second term of this derivative is plus e to the minus I over h bar h0t times I h bar time derivative of now the state phi of t. Okay, so then of course there is a way to synthesize this a little bit, which is, since this is equal to 1 here, so then this is nothing but this and this, they commute. We have seen that and much more for the time independent Hamiltonian. So then this is nothing but e to the minus I over h bar h0t times h0 acting on phi of t plus e to the minus I over h bar h0t times IH bar time derivative of the state phi. So this is what we got, and then so what are we going to do with this? So what we're going to do with this is that we're going to replace that in this expression number 2 that I label as 2 here, and there of course the idea is just to derive Schrödinger equation in terms of W of t. Okay, so then that's what we're going to do now. So then we write again. Now let's use blue. We write again the Schrödinger equation that we had upstairs, h0 plus W of t acting on psi of t equal to IH bar time derivative of psi of t. Now what we do is that we replace, of course, this what we just calculated here in red. Let's see, what is it? Yeah, this, we calculate that in red, so we replace that, and as well of course we replace the ansatz for our state, which is this one. So then that's what we have to more or less remember. So then let's write it down here. Psi of t is equal to e to the minus I over h bar h0t times phi of t. Okay, so then that means that this expression here becomes h0 plus W of t times e to the minus I over h bar h0 t acted on phi of t. This equal to what we have here in red, which is e to the minus I over h bar, okay, h0 t h0 phi of t plus e to the minus I over h bar h0 t I h bar time derivative of the state phi of t. Okay, now we can see immediately something. So here, let me use purple to just show you something. Here we have h0, we have e to the minus I over h bar h0 t on phi of t. Since h0 and since this exponential containing h0 and h0 commute, so we actually have the very same thing that we have here. So then this term goes and this term goes, so then we are just left with W of t times e to the minus I over h bar h0 t acting on phi of t is equal to e to the minus I over h bar h0 t times I h bar time derivative of phi of t state. This is actually our equation, and we just need one more step to simplify this in the way we want. So we multiply both sides by e to the plus. So we multiply here e to the plus I over h bar h0 t, and we do the same here. E to the I over h bar h0 t. So then here these two cancel. Here they don't cancel because in general w of t doesn't commute with h0. So what we end at is e to the I over h bar h0 t w of t e to the minus I over h bar h0 t, that acting on phi of t, equal to I over h bar time derivative of phi of t, and this is the Schrödinger equation for our perturbation w. Okay, so then it's just as simple as this. Now then you might wonder, okay, what is the interaction picture? So the interaction picture is a picture in which the perturbation evolves in time according to the non-interacting Hamiltonian, or to the Hamiltonian that does not contain the perturbation, which is this. H0 is the free Hamiltonian, and W of t is the perturbation. Okay, so now W sub I of t is the perturbation in the interaction picture, and what this is just a time evolution of this perturbation according to the free Hamiltonian. That's what that is. So then we define that in this way: e to the I over h bar h0 t times W of t, which is in the Heisenberg representation, times e to the minus I h bar h0 t. So then to have an operator in the interaction picture, you need to split your Hamiltonian into two parts. A part that contains the perturbation, and a part that is perturbation free. And when the part that contains the perturbation, that we call W of t, evolves in time according to the perturbation free part of the Hamiltonian, according to this rule, then we said that the perturbation is written in the interaction picture. Okay, so then what does that mean in general? That this equation here that we have in purple, in the interaction picture, is Wi of t phi of t equal to IH bar time derivative of phi of t. This is in the interaction picture. Okay, so then now it is useful, because let's remember that we're talking about linear response. It is useful to express the perturbation Hamiltonian in the interaction picture in the following way. So then we're going to say that that perturbation in general will have the following form. So in the Heisenberg picture, let's start from the Heisenberg picture. Usually there are some books that write this as some Hamiltonian H prime, which contains the perturbations times some adiabatic decay factor where delta tends to 0. So this just guarantees that the perturbation is turned on adiabatically. You can remove it or you can leave it there. I mean, it's up to you. It doesn't affect really much the calculation. And then following Fu Xianhan, the author of quantum theory of solids. So then we write H prime of t in the following form. We said that is e to the delta t divided by the volume times the integral of some scalar field f of r comma t times some operator b of r d3r. Okay, so then the actual operator in the Hamiltonian representative perturbation is b. This is just a scalar. Okay, so then, and the idea in linear response is to determine this operator being the perturbation, how will affect a given response that we want to evaluate in the linear regime. So then that means that there will be a response that will depend linearly with b, and that we will be able to evaluate how this operator b affects that other operator that we want to analyze, whose response we want to analyze. That will be more or less the lexic that I should use now. So then in the interaction picture I can write now the following. This is equal to e to the minus I over h bar h0 t w of t. Sorry, this shouldn't be here because I already included in the definition above. So just sorry about that. So this should be a 1 here. So then this is w of t. This is let's go back here. This is a plus. This is e to the minus I over h bar h0 t. And this is nothing but e to the I over h bar h0 t. Now we write this in integral form. Now this one here does contain this adiabatic factor divided by volume f of r comma t operator b of r d3r, and all of it multiplied by e to the minus I over h bar h0 t. Now what can we do here? So this is a scalar and this is a scalar too, so then this all commute with this one here, and we can put this one inside as well. We can put this one here, so then w sub I of t, which is the perturbation in the interaction picture, reads e to the delta t divided by the volume integral of f of r comma t e to the plus I over h bar h0 t operator b of r times e to the minus I over h bar h0 t d3r. Now then what is this? This is nothing but e to the delta t divided by v integral of f of r comma t b. Now this is b sub I of r comma t, because now it's in the interaction representation, this operator here d3r. and this is equal to the perturbation in the interaction picture. Okay, so then pretty much in the interaction picture what we have is that the Hamiltonian that we have defined above, h prime of t in the interaction picture, will be 1 over v integral of f of r comma t b sub I r comma t in the interaction picture d3r. Okay, then this will allows us to calculate the response of a given operator in our quantum mechanical system to the application of this operator b of I, and then from there we can construct our formalism of linear response theory. Now we will do some perturbation theory on the interaction Hamiltonian, and we will proceed from there. Thank you.